Hi there. So now we're turning our attention to energy. Energy is a really important concept in chemistry. And for example, you can see here a chemical reaction where solid carbon in the form of coal is burning in air, so combining with oxygen, and the reaction produces a large amount of heat, which is being used to heat up a metal bar. And so, understanding how heat is involved in chemical reactions and in other aspects of matter is going to be a really important part of our studies of chemistry. So, if you've encountered some of the ideas in physics before, you may have encountered two types of energy: kinetic energy and potential energy. Kinetic energy is energy of motion, and so this, for example, shows up in objects like this racing car that are moving at some speed. In chemical contexts, kinetic energy most often shows up in movement of molecules, especially in fluids like liquids and gases. Molecules can have a lot of kinetic energy. Another place where you see kinetic energy in mechanical situations is in reciprocating or vibrating motion. For example, in an internal engine in an automobile, and in chemical systems, we often see this as vibrations of molecules. And so both of these are examples of kinetic energy, energy that is due to the movement or the motion of objects or molecules. And kinetic energy shows up directly in the temperature of objects. So the relationship is a little bit complicated, but a very good rule of thumb is that high temperature is correlated with high kinetic energy. And so, as the temperature of an object increases, the kinetic energy of the particles in that object is getting higher and higher. Now, potential energy is energy associated with the position of an object. So, for instance, rocks that are at the top of the cliff here would have a higher potential energy than rocks further down. And that energy is associated with gravity. You can also have potential energy associated with things like the shape of an object. For example, a compressed spring in a shock absorber has a lot of potential energy that's stored in that spring. Now, in chemical systems, the potential energy shows up mainly in the arrangement of atoms and molecules. So, for instance, liquid water has a fairly random arrangement of water molecules, and if those water molecules were to come into a more orderly arrangement and form a crystal, that would be a lower potential energy. Just like the liquid water, that arrangement of molecules would be analogous to the compressed spring or to the rocks at the top of a cliff. The water molecules in the ice crystal would be analogous to a relaxed spring or to the rocks at the bottom of the cliff. And one thing that's really important about kinetic and potential energy is that they can be interconverted. So if you think about water falling off a cliff in a waterfall, at the top of the cliff, the water has a relatively high potential energy and a low kinetic energy. So it's up high, it has a high potential energy, but it's not moving very fast, it has a low kinetic energy. And as the water falls, it picks up speed, it goes faster and faster, but it's moving down, and so it's losing potential energy as it falls, but it's picking up speed, so it's gaining kinetic energy. And so at the bottom of the waterfall, the water has a low potential energy, but a very high kinetic energy. So the total amount of energy is unchanged, energy is conserved, but here it's being converted from potential energy into kinetic energy. Now, when the water actually hits the bottom of the waterfall, it stops moving. But what happens to all that kinetic energy that it had in its movement? Well, the answer is all the kinetic energy that the water had as it was falling down the waterfall, when that when those water droplets hit the water at the base of the falls, all that energy gets scrambled up and gets turned into kinetic energy of the individual water molecules. And that shows up in the temperature of the water. So if, for instance, the water at the top of the falls had a temperature of 22.0 degrees Celsius, if the falls are very high, this particular waterfall is almost a kilometer high, and so the water is moving fast enough that when it hits the bottom and all that energy gets scrambled up, it warms up the water by about 2.5 degrees Celsius. But again, this is a conversion from potential energy into kinetic energy. Now, before I go on, it's possible that you're like this guy from the IKEA instructions, and you may be wondering why chemists would be so concerned with energy. After all, chemistry is the study of matter. But matter and energy are inextricably connected, and there are a number of practical as well as theoretical reasons why energy is very relevant to chemists. For one thing, matter can be used to store and release energy, and so it's a vital part of our industrialized civilization. We make use of energy all the time, and so being able to store that energy and release it on command is really important. And also, matter itself is affected by energy. So think about baking a cake. When you put cake batter into an oven, the oven is dumping energy into the cake batter, and that converts it into a cake. And so their matter is being affected by energy. And then there are theoretical reasons. Most importantly, by studying energy, that gives us information about the inner workings of matter. So we can learn about how atoms and molecules work by studying the energy that's involved in the things that they do. Okay, so the rest of this video is going to be concerned with a particular facet of energy, and that is heat. So heat, which is represented by the symbol Q, either lowercase or capital Q, is defined as the energy that's transferred from a hotter to a cooler body due to a temperature gradient. So basically, energy that's transferred from a hot object to a cold object is called heat. If you're wondering where the letter Q comes from, it comes from an early scientific publication where Q was used because it represented the quantity of heat involved in a process. And so an example of heat, if you put a piece of cold ice cream onto a hot piece of apple pie, heat will flow from the hot apple pie into the cold ice cream. And that represents a transfer of energy from a high temperature to a low temperature. And heat is a quantity. It does have units. The SI unit for heat is the joule, named after James Prescott Joule, who did a lot of important work in studies of heat and energy. That's the SI unit. That's the unit in the metric system. An older unit that still sticks around quite a bit is the calorie. The calorie is equal to 4.184 joules, and the calorie was a unit that was based on water. So originally a calorie was the amount of heat that it took to raise the temperature of 1 gram of water by 1 degree Celsius. And in more modern units of joules, a calorie is equal to 4.184 joules. Now, you may have heard the word calorie used in the context of food. In food science, calorie is actually a kilocalorie. So calorie with a capital C is the way that the word calorie is used in referring to food, and it's equal to 1,000 normal calories, or 4,184 joules. So you still encounter both types of calorie in everyday use, but in scientific work, the SI unit of joule is preferred. Now, like I said, heat is a quantity, but it's not something that we can measure directly. So even though heat flows from a hot piece of apple pie into a cold piece of ice cream, we can't actually measure that heat flow directly. What we can measure is the temperature of the apple pie and the ice cream. And by measuring the temperature of an object, that gives us information about the heat flow. And that's what I want to look at next. So the way to see precisely how heat flow and temperature are related, consider an electric heater. So if you take a piece of wire and run electric current through it, the wire will heat up, and you can immerse that hot wire in a container of water, for example, and as the temperature of the wire increases, the hot wire will transfer energy into the water and warm up the water. This is the kind of technology that's involved in an electric water kettle, for instance. And so I sat down the other day and actually measured the temperature of water in my kettle over time as I had the heat turned on. And what I found is that as the heating continued, the water in the kettle got hotter, and the temperature change got bigger and bigger and bigger the longer I heated the water. And the heating time, I can actually turn that into a measure of the amount of heat, because I know that the kettle that I used has 1,500 watts. And so that tells me that every second that kettle is turned on, it is dumping 1,500 joules into the water. So a watt is a joule per second, and so 1,500 watts is 1,500 joules per second. And so I can translate the heating time into an amount of heat that's been added to the water. And for convenience, I'm expressing that as kilojoules. So every second, this particular kettle transfers 1.5 kilojoules of heat into the water inside the kettle. Now, if we're interested in how we can learn about the heat from the temperature change, we're going to want to flip this graph around and put the temperature change on the x-axis and heat on the y-axis. So I've done that. Let me clean up the text here to make it a little more readable. So again, I've got the temperature change of the water on the x-axis. The amount of heat that was added is on the y-axis. And so here you can see that larger temperature changes are associated with larger amounts of heat. And this particular set of data corresponds to the temperature of 500 grams of water in the electric kettle. So a container like this, which is being used for measurements of heat and temperature, is formally called a calorimeter. And so these blue dots here represent the heat added to the calorimeter and 500 grams of water. Now, if there were more water in the kettle, you would expect that it would take more heat to raise the temperature. And that's exactly what happens. So I ran this experiment again with 1,000 grams of water in the calorimeter and found that I needed not quite twice as much heat. And it's not quite doubled because the kettle itself isn't changing, but the water. So the kettle is absorbing some heat, and the water is absorbing some heat, and so the amount of heat that's going into the water is actually doubling when you go from 500 grams to 1,000 grams. And like I said, the relationship between the amount of heat that's added and the temperature change is more or less a straight line. So we can draw a straight line through these data. And this is pretty typical. If you take an object and you add heat to it, its temperature will increase more or less in proportion to the amount of heat that you add. So there's a direct proportionality between the heat that's added to an object and its temperature change, at least for small changes in temperature. And we can express that proportionality as follows. The heat that flows into an object is proportional to the change in temperature. So Q, again, is our heat. And the constant of proportionality that's the letter C in this equation. That is called the heat capacity of the object. And so objects with a higher heat capacity require more heat to raise the temperature. So the kettle with 1,000 grams of water in it had a higher heat capacity than the calorimeter with only 500 grams of water. And so, an object like the kettle itself has a certain heat capacity, and then the water in the kettle also has a heat capacity. And we can express the heat capacity of a substance like water in terms of its specific heat. So the specific heat of a substance is its heat capacity per gram. And so the way that this figures into heat calculations is heat capacity times the change in temperature, and then the heat capacity is going to be the specific heat, the heat capacity per gram, times the number of grams. So we can also write down that the heat that's needed to raise the temperature of an object is equal to its specific heat times the mass in grams. And specific heat has been measured for all kinds of different substances. Here's a small list of substances and the various specific heats. And the values for specific heat vary over quite a range. And I'm not going to dwell on any kind of patterns in the heat capacity, except to a limited degree. But for now, I want to show you how we would use specific heat to actually calculate the heat that's associated with a temperature change. So, for example, the heat that's needed to raise the temperature of 30 grams of iron by 5 degrees Celsius, in order to find that, we would take the heat capacity of iron, which is 0.449 joules per gram per degree Celsius. We multiply that by the number of grams of iron, in this case 30.0 grams, and then multiply by the change in temperature, 5.00 degrees Celsius, and multiplying all that out, the grams cancel, the degrees Celsius cancel, and we are left with 67.4 joules of heat. And so think about what we just did here. What we did was we can measure changes in temperature using a thermometer, and by doing a calculation like this, we can turn that temperature change into a measurement of the amount of heat that flowed into the iron. And so knowing the specific heat of a substance gives us a way to use a thermometer as a heat meter. So we can indirectly measure the heat that flows into or out of something simply by measuring its temperature change. And that's something that's really useful to do, and that'll be the focus of our next video.